last lecture, we had obtained a physical interpretation of the wave function. The Schrodinger equation is written in terms of the wave function psi, and we had said we had derived an equation of continuity from which we could interpret mod psi square d tau as the probability of finding the particle between in the volume element d tau. Actually, we obtained that this should be proportional to the probability. But then if we normalize this in the entire space, so then we can interpret mod psi square d tau as the probability of finding the particle in the volume element d tau. So, associated with the particle, if I want to find out the expectation value of any quantity x, then I just have to multiply by the probability density function and integrate over the entire space. Actually, the integration is something like this, that all the integration is over the entire space x mod psi square d tau divided by integral mod psi square d tau, because mod psi square d tau is proportional to the probability. But if this integral is 1, which we will assume from now onwards, so we will assume from now onwards that the wave function psi is normalized, and if the wave function is normalized, then mod psi square, this integral over the entire space is 1, and so therefore, the denominator is 1. So, I will obtain x psi star psi, and I will write this for reasons which will become clear in a moment as x is equal to integral psi star x psi d tau. Why do we write in this particular way? It will become clear in 1 minute. Now, we had the time dependent Schrodinger equation, the 3-dimensional Schrodinger equation, I h cross delta psi by delta t is equal to minus h cross square by 2 m del square psi plus v psi. What I do is that I multiply this equation by psi star and then integrate. So, I obtain on the left hand side, please see this carefully, this integration is over the entire space. So, the integral is really a 3-dimensional integral, psi star multiplied by I h cross delta by delta t into psi d tau, the integration is over the entire space, and then we will have psi star multiplied by minus h cross square by 2 m del square psi d tau plus psi star v times psi. Now, the last term, this term is just the potential energy function multiplied by the probability density function integrated over the entire space. So, this quantity is the expectation value of the potential energy. Classically, we know that the total energy is the kinetic energy plus the potential energy. So, we should expect that the expectation value of the total energy must be equal to the expectation value of the kinetic energy plus the expectation value of the potential energy. So, therefore, this quantity should be the expectation value of the total energy and this quantity should be the expectation value of the kinetic energy. And now we see that the quantity within the bracket, within the two brackets, is the operator corresponding to the energy E. Similarly, P square is Px square plus Py square plus Pz square. So, this is minus h cross square by 2 m delta 2 by delta x square plus delta 2 by delta y square plus delta 2 by delta z square. So, this quantity within the brackets is the operator corresponding to P square by 2 m. So, therefore, we get the recipe that if I want to find the expectation value, for example, of Px, then what I have to do is I will write down psi star Px psi d tau, where Px is the operator representation for Px. So, therefore, from above we obtain the recipe that if I want to find out the expectation value of x, y or z, then this is equal to all these integrals are 3-dimensional integral psi star psi x d tau, they are normalized. Similarly, for y, similarly for z. For Px, the expectation value of Px is equal to psi star Px psi d tau, which is equal to psi star minus I h cross delta psi by delta x d tau. If I want the expectation value of Px square, then Px square as we know is Px times Px. So, minus I by h cross delta by delta x into minus I h cross, that is minus h cross square delta 2 by delta x square. So, Px square, the expectation value is psi star minus h cross square delta 2 psi by delta x square. And the general recipe, if I want to measure a dynamical variable O, then the expectation value of this, I represent that by the corresponding operator and put between psi star and psi O psi d tau. This is the general recipe for determining the expectation value. So, therefore, we must remember these 2-3 equations. The expectation value is of course very simple. The expectation value of Px is psi star on the left and psi on the right, with Px represented by its differential operator representation, and this is for Px square and if you want to write the kinetic energy, then I just have to divide by 2m. In general, if I want to make a measurement of a dynamical variable represented by O, and if I want to find out the expectation value, then all that I have to do is to integrate psi star O psi d tau. I am assuming that the wave function is normalized. With this, we will try to give an exact formulation of the uncertainty principle between x and px, that in statistical theories, if there is a variation of a parameter, then the spread is measured in terms of mean square deviation, and that is delta x is defined as x square, the average of x square minus x average square under the root. So, this is the spread, the uncertainty in x. Now, for example, let me give you an example of an experiment. I am measuring the acceleration due to gravity. I use a simple pendulum, and in 3 random measurements I change the length of the pendulum, and in 3 random measurements I get 979 meter per second square, 980 and 981. The mean of that is 980 centimeter per second square. Now, I use a Cater's pendulum to make a measurement of acceleration due to gravity, but there I get 3 values like this: 979.9, 980.0 and 980.1. Now, if I take the mean of that, I will again get 980, but there is a difference between these two. Here the uncertainty is much more than this. Here the uncertainty is of the order of 1, and here the uncertainty is of the order of 0.1. How do we express this uncertainty? This we express in terms of carrying out. Let us suppose the spread will be, you will write down what is the average value of g square minus the square of the average value, and then take the square root. In this case, it will come out to be 0.8 or 0.9, and in this case, it will come out to be 0.08 or 0.09, 0.1 about, something like that. So, the spread, the variation, if I make a large number of measurement, the variation is usually expressed by this quantity delta x. I take the average of the square minus square of the average. Similarly, if I make the measurement of the momentum, then I will write it as the square root of the average of the square of the momentum. I am considering only the x component. I am only considering the x component. So, px square minus px whole square. I will show that for any wave function, the product delta x delta px is greater than or equal to h cross by 2. So, this is an exact statement for the uncertainty relation. Now, in order to derive that, we will first prove an inequality, and this is known as Schwarz's inequality, and the inequality is I have f star f d tau multiplied by g star g d tau, where all functions f and g are well behaved square integrable functions. This is always greater than or equal to 1 by 4 brackets integral f star g plus f g star d tau whole square. Now, this quantity we denote by A, this quantity we denote by C, and we write down that B is equal to integral f star g d tau. Therefore, B star is equal to the complex conjugate of this is f g star d tau. All these integrals are over the entire space, and they are all 3-dimensional integrals. Now, in order to prove this inequality, where f, g are all arbitrary functions, arbitrary means single valued and integrable functions, and in order to prove that, I consider a parameter lambda which is real, lambda I assume to be real, and I consider the integral lambda f plus g mod square d tau. Now, since lambda is real, so this quantity is positive because it is the square of the modulus and integrated over the entire space. So, this must be always greater than or equal to 0, positive, always positive, because this is the integrand is a positive definite quantity. So, let me write down the integrand. So, that is equal to lambda f plus g multiplied by lambda f star plus g star, because lambda is itself a real quantity. So, I multiply this out. So, I get lambda square f star f, I can write one before that, plus lambda times f star g plus f g star plus g star g. So, I integrate this d tau, and this is always positive definite. So, I integrate it here, I integrate it here, I integrate it here. All integrals are over entire space. So, this is always positive definite. So, this is A as I had written down here, and this is B plus B star, and this is C. So, I obtain lambda square A plus lambda B plus B star plus C will be always greater than 0. This means, if you plot this as a function of lambda, it will have no zeros, and so therefore, for example, as you will know that, you see, if I consider an equation like this, a x square plus b x plus c, the roots of this equation are x is equal to minus b plus minus under root of b square minus 4 ac divided by 2a. But if this quantity is always positive, then there are no real roots, and so therefore b square must be less than 4 ac. So that this quantity is negative, and therefore it will have no real roots. So this quantity b plus b star whole square must be less than or equal to 4 AC. So you get AC must be greater than 1 by 4 b plus b star whole square, and that is my inequality, that f star A was equal to f star, that is f star f d tau, C was equal to g star g d tau. This must be greater than 1 by 4 b plus b star whole square, that is integral f star g plus f g star d tau whole square. So therefore, we have been able to derive what is known as Schwarz's inequality. Now, we assume that f is equal to p psi, and p psi is equal to minus I h cross delta psi by delta x, and g is equal to I times x psi. Then you can see, we will discuss the easiest case first. G star g d tau, g star g d tau, g star will be I times minus I is plus 1. So, this will be g star will be x into psi star. So, this will be psi star x square psi d tau. So, this is the expectation value of x square. We are considering the special case, although the more general case can be considered very easily, that the expectation value of x is 0. I can always choose the origin in such a way that the expectation value of x is 0. We further assume that the expectation value of p x is 0. So, g star g d tau I x psi multiplied by minus I x psi star. So, I times minus I becomes 1. So, psi star x square psi d tau. So, this is the expectation value of x square. Similarly, f star f d tau will be equal to, if you see this, f star will be I h cross delta psi star by delta x multiplied by f, that is minus I h cross delta psi by delta x multiplied by d tau, that is dx dy dz. So, I times minus I is 1. So, minus 1. So, h cross square, if I take outside h cross square, and I just consider the x part of the integration, the y and z part are also there. So, I get delta psi star by delta x into delta psi by delta x dx, actually into dy into dz, but I am omitting that at the moment. So, this I integrate by parts and I obtain h cross square. This I take as the integrating factor psi star delta psi by delta x from minus infinity to plus infinity minus integral psi star delta 2 psi by delta x square dx, of course multiplied by dy dz, and dy dz integrations are also there. Now, for a localized wave packet, for a particle which is localized in a small region of space, the wave function has to vanish at infinity. So, this term vanishes at the upper and the lower limit, and I obtain only this. So, I finally obtain integral f star f d tau is equal to psi star minus h cross square. I take this inside delta 2 psi by delta x square dx, similarly dy and dz. So, this is the expectation value of px square, because you remember that px is minus I h cross delta by delta x, and px square will be minus I h cross delta by delta x. So, px square psi is minus I h cross delta by delta x into psi. So, this will minus minus plus h cross minus minus plus, and then I square is minus. So, this is equal to minus h cross square delta 2 psi by delta x square. So, this quantity becomes the expectation value of px square, but I will just write p square. And then the third term on the right hand side will be, if you remember, so therefore, f star f d tau is p square, g star g d tau we had just now obtained, g star g d tau was equal to x square. The term on the right hand side, you see in the inequality we had 1 over, this is f star f, this is g star g is greater than or equal to 1 over 4 f star g plus f g star. So, let me evaluate this. So, f star g, let me do it on a fresh page, that 1 by 4 integral f star g plus f g star, again d tau is dx dy dz. So, f, as you may recall, was equal to minus I h cross. So, f, as you may recall, was minus I h cross delta psi by delta x, and g was equal to I x psi. So, we will have, so let me just consider the integrand. The integrand is equal to 1 over f star g plus f g star and this is equal to 1 over 4 f star, that is I h cross delta psi star by delta x into G, that is I x psi plus f, that is f is minus I h cross delta psi by delta x. You have to do this little carefully, and G star is minus I. So, minus minus becomes plus. So, I x psi star. So, this is I times I is minus 1, and this is I times I is minus 1. So, this becomes minus h cross by 4 delta by delta x psi star x psi plus delta psi by delta x x psi star. Now, if you write down this equation, this expression delta by delta x psi star x psi, then this will be, please see, delta psi star by delta x into x psi plus psi star into, please see this carefully, delta by delta x of these two terms, the product of these two terms. And if I differentiate this, first, I will get psi, because the differential coefficient of x is 1 plus x delta psi by delta x. So, you obtain, if you, these two terms are appearing here, if you see this carefully, this is delta psi star delta x multiplied by x psi plus psi star psi plus psi star x delta psi by delta x. So, if you see this term is this term, let me encircle them with red. So, this term is the same as this term, and this term is the same as this term. So, this plus this, which is the quantity inside the square brackets here, is this minus this. So, therefore, the integrand will become, minus h cross by 4 delta by delta x. One has to just patiently work this out. It is straightforward, but it requires a little patience, minus psi star psi. If I integrate this, so I have to integrate, if I had to integrate this with respect to x and this with respect to dx and then dy dz, then the integration over x will be psi star x psi from minus infinity to plus infinity. So, the wave function is going to vanish at both plus infinity and minus infinity. So, therefore, this term will be 0 and if the wave function is normalized, so psi star psi d tau is 1 if the wave function is normalized. There is a minus sign sitting outside, so you will get h cross by 4. So, you will get the relation that if I substitute that in a let me put it that f star we had obtained that f star f d tau multiplied by g star g d tau is greater than or equal to 1/4 of this integral f star g plus f g star d tau whole square. So, you will obtain, that that this was equal to, if I remember it rightly, that one was g star g was equal to I had found that out, g star g was equal to x square and this was equal to p square. So, as you know that delta p is equal to under root of p square minus p average whole square. I am assuming p average to be 0. So, therefore, this is equal to, I am taking the special case of p average being 0. So, this is square root of p square and delta x is equal to under root of x square minus x average square, which is under root of x square. I am assuming I can always choose the origin of my coordinates such that the x average is 0. So, this from, if I substitute this here, I will get the uncertainty relation that delta p delta x is always greater than or equal to h cross by 2. This is the uncertainty relation that we have proved from the first principles. And let me give you a few examples. So, from the Schwarz inequality, which is written here, we have, and then by assuming that f is given by g is given by ixi, g was equal to ixi, and similarly we had assumed an expression for f. We have been able to prove that only thing that we have assumed is that the expectation value of p is 0 and expectation value of x is 0. But expectation of value of x is 0 does not mean anything, because you can always choose the origin to be such that the expectation value of x is 0, but expectation value of p is 0. One can also generalize this for the case when the expectation value of p is not equal to 0. Now, let me go back, having proved the uncertainty principle, let me go back to a simple wave packet. So, the simple wave packet is a one dimensional packet that we had considered, that psi of x is equal to, I consider this as a superposition of plane waves under root of 2 pi h cross minus infinity, a one dimensional wave packet, a of p e to the power of I by h cross p x dp. Now, the expectation value of p, as we had discussed earlier is equal to psi star p psi, where p is the operator representing p, the variable p. And as we all know now, that what we have been discussing, that this is equal to minus I h cross psi star delta psi by delta x dx. So, what I do is I substitute for psi star here, I substitute for psi here. It is little complicated, but if you work this out, it is worth it. So, psi star will be complex conjugate of this. So, let us do this carefully. I h cross and then 2 pi h cross will come here, 2 pi h cross, and now there are 3 integrals, one for psi star, another for psi, and the third one is on dx. So, please see this. First integral is over dx going from minus infinity to plus infinity. Then we write down the expression for psi star. Psi star will be 2 pi h cross, I have already taken outside. So, this will be a star p e to the power of minus I by h cross p x dp. The limits are from minus infinity to plus infinity. And then delta psi by delta x. So, let me do it with a red pen. So, 2 pi h cross I have already taken outside. So, I will have minus infinity to plus infinity. If I differentiate with respect to x, then I will get a p inside. So, I get p times a of p e to the power of I by h cross p x dp. Now, here I have to be very careful. Till now it is all right. If I first integrate this and then integrate this and then carry out this integration, but I am going to jumble up the integration. Then this p has to be distinguished from this p. And so, therefore, I put a prime here. Now, I can write all the 3 integrals together. Then this p prime will not get confused with this p. So, let me write it down that this p will be equal to minus I by h cross by 2 pi h cross I carry out this dp and then dp prime, collect all the terms which involve only p and p prime, and these are a star p prime, p a of p, and then there is an integral over x. Let me write this down. What is the integral over x? So, the integral over x is minus infinity to plus infinity dx e to the power of I by h cross p x minus p prime x dx. So, if I take the factor 2 pi h cross, this will be minus infinity to plus infinity, I am sorry, I have written dx twice. So, e by e to the power of I by h cross p minus p prime into x into dx, and this, as you know, is delta of p minus p prime. So, therefore, in this integral, I have taken this factor here and this factor, this integral, and I will obtain minus oh, I am sorry, that is what I made a mistake, that when I differentiated delta psi by delta x, I will not get just p, I will get I by h cross p. So, this will be I by h cross here, sorry. So, I by h cross, so that I will multiply by I will become minus 1 and this will become plus h cross h cross. I hope you understand what I am trying to say, that we had here delta psi by delta x, and when I differentiate this with respect to x, then I will get an I by h cross times p into e to the power of I by h cross px. So, I had forgotten the factor I by h cross. So, I times I is minus 1, minus minus is plus, and the h cross will cancel out with this, and then so this two factors will go away and this will become plus and this will become 2 pi h cross. Now, this 2 pi h cross I have taken here. So, I will obtain for expectation value of p this remarkable result, that minus infinity to plus infinity dp, and if I write down p, the AP star A star p prime, then delta of p minus p prime dp prime. So, if I carry out this integration over p prime, then this is just A star p. So, I get this as minus infinity to plus infinity dp p mod ap square. So, we have for any wave function psi, if I write as 1 over 2 pi h cross integral A p e to the power of I by h cross p x dp from minus infinity to plus infinity, then the expectation value of p will be given by psi star p psi, that is minus I h cross delta psi by delta x into dx, and if we just carried out the entire manipulation, entire algebra, and we found that this is equal to p into a of p mod square dp. So, therefore, similarly, if I calculate p square, I will find that this is equal to minus infinity. I leave this as an exercise, you have to differentiate this twice. It is very easy, it is very straightforward, and you will have a p square dp. Thus, we can interpret a p square dp as the probability of finding the momentum between p and p plus dp. I must add, probability of finding the x component of the momentum between p and p plus dp. So, therefore, this is also physically obvious, because what is an integral? Integral is the superposition of these wave functions. And so, therefore, in this case this represents the momentum spread of the wave function. The quantity A p square represents the momentum spread of the wave function. So, if a particle is localized within a distance of the order of sigma, if this is the wave function, then the corresponding momentum spread function A of p mod square, this is say mod psi square, the mod p A p square will be localized also within momentum spreads function will be of the order of h cross by sigma. So, therefore, we wrote down the 2 turns back, we wrote down for the free particle, the most general solution was given by this of the time independent of the time dependent Schrodinger equation. And here A p represents, we have now physically interpreted, A p represents the momentum distribution function. And this is how, from the given form of psi of x, I can determine the corresponding A of p by taking the inverse Fourier transform and interpret psi of x mod square dx as probability of finding the particle between x and x plus dx, and A p square dp will be the probability of finding the particle, of finding the momentum between p and p plus dp. I conclude today's talk by writing the wave function, which is psi x at t equal to 0, let us suppose. We wrote down that we considered this 2 turns back, pi sigma 0 square raised to the power of 4 e to the power of minus x square by 2 sigma 0 square e to the power of I by h cross p naught x. If you calculate this, first of all, you can easily show that minus infinity to plus infinity mod psi square dx is 1. So, the function is normalized. I have done this quite a few times, I do not want to do it. Secondly, the expectation value of x will be x times mod psi square dx. So, mod psi square will be e to the, I can write down under root of pi sigma 0 square and then x into x e to the power of minus x square by sigma naught square. The mod square of this function, this will become 1 and this will become e to the power of minus x square by sigma. These limits are from minus infinity to plus infinity, and of course, this is an odd function of x, and so therefore, the integral is 0. So, the expectation value of x is 0. The expectation value of x square is x square here, x square here, and here you can easily integrate this in terms of gamma function, and then you will get 1 over under root of pi sigma 0 square 2 integral 0 to infinity, and then if you put x square is equal to say y and then carry out the integration, you will obtain this to be equal to sigma 0 square by 2. So, we had x average is 0 and x square average is half sigma 0 square. So, therefore, uncertainty in x will be under root of x square minus x average square. So, this is 0. So, this will be sigma 0 by root 2. This is the uncertainty, that if you make a measurement of the x coordinate of the particle, then it will be, I showed you a wave packet. So, the wave packet is such that it is localized within a distance of sigma 0. Now, for the wave function that I had written down, for the wave function I can write it as equal to 1 over 2 pi h cross integral a p e to the power of I by h cross p x dp, and then take the inverse Fourier transform of the function, and you will finally get a p is equal to sigma, I leave that as an exercise, sigma 0 square raised to the divided by pi h cross square raised to the power of 1 by 4 raised to the power of 1 by 4 e to the power of minus p minus p 0 whole square sigma 0 square by h cross square. So, this is, if you plot the momentum distribution function, then you will find that p mod a p square dp, this will be the average value of p, this will come out to be p 0, and average value of p square will be p square this thing, and if you carry out this integration, one can show that this will come out to be p 0 square plus h cross square by 2 sigma 0 square. So, delta p will be this minus square of this. So, delta p will be under root of h cross square by 2 sigma 0 square. So, this will be h cross by root 2 sigma 0. So, if I take the product of the two, so delta p delta x will be of the order of h cross of 2. So, the uncertainty principle is contained in the solution of the wave function. So, I end by showing the wave packet that I had shown last time, that this is the, let us suppose I increase the, so the particle is described by this wave function which evolves with time as shown in this diagram, as shown in this in the evolution of the wave packet. The particle is localized somewhere here, and as it propagates, it broadens with time. That I have not explicitly shown, but you can carry out the calculations and show that how the wave function will evolve with time, and at each step the product of delta x and delta p is always greater than h cross by 2. So, we have considered the definition of the uncertainty principle. We have proved the uncertainty principle, given a physical interpretation of the wave function through the equation of continuity, and interpreted the wave function corresponding to a Gaussian wave packet. Thank you.